Okay, so today is the last lecture, and we're going to talk about optimization. So this is going to combine mostly things from the vector calculus lecture with new notions about the shape of functions and kind of algorithmic considerations about how to optimize functions. So we're going to focus on continuous optimization, and you can call that also numerical optimization. So there are different kinds of optimization techniques. One of the big other kind would be kind of like black box optimization, in which you have very loose assumption on the kind of smoothness of the function that you're optimizing. It might be completely not smooth, and then you're trying to find maybe a global optimum. And the way these usually work is they only use point information. So they just sample points and they query the function at specific points, and they combine this information in some way in order to provide like what would be the next best guess or the most informative guess. And we're not going to talk about this today. Today we're going to focus on the case where we have continuity assumption on the function that we're optimizing. So we are basically thinking that the first order and the second order derivative are continuous and that we can query those. Of course, you can always, and we saw that in the numerical optimization, in the vector calculus lecture, you can always approximate continuous derivative by finite differences. We also saw that in the differential equation lecture. In the exercise lecture, we actually built this matrix that, given sample points, was extracting the first order or second order derivative of the function. So yeah, so numerical optimization basically considers that the function is continuous or smooth, and then develops a bunch of techniques that can be used in these cases. Yeah. So why would we use numerical optimization? So the thing in machine learning is to use it offline, where we are typically in supervised learning given a data set of associations between input and output that we want our decision algorithm to make. And the numerical optimizer is going to help us basically minimize the loss function, which is going to make our model, kind of reduce the risk, the empirical risk that we measure on the data set, the training set that we're having. So that's like offline, using numerical optimization to learn. Numerical can also be, optimization can also be used online, and that's the idea of making optimal decisions. So the idea is you model your problem, like a trajectory optimization problem, for instance. You model your problem with a cost function, and then you're trying to minimize or find a solution that minimizes the cost that you associate with a certain problem. I think in the linear algebra lecture, what we saw was some kind of optimal decision problem that we could model with a linear combination of equations, and then we saw there's like a closed form solution. We just inverse the matrix, and we have our solution, or use the pseudo inverse when the matrix is not square, and so we have more decision variable than state variable, or the inverse. So more state variable than decision variable, depending on whether it's tall or fat. And so these are kind of optimal decision-making problems. But we can model optimal decision problems in using continuous functions, and then we'd use numerical optimization to find optimal solutions for those. We'll talk about in which cases does numerical optimization just solve the problem entirely, and this is the realm of convexity, so cost functions and constraint functions that are convex, and we'll define what that is. When things are not convex, then we just have to be satisfied with a local optimal solution most of the time. So the objective function kind of formalizes the notion of what is good. So in learning, that would be the risk, or the empirical risk, and in optimal control, this might be all sorts of different things. So yeah, in optimal control, it's the cost function. In machine learning, it's the loss function. In unsupervised learning, this might be a probabilistic model that we are trying to maximize. So we're basically trying to maximize the likelihood of the data under the probabilistic model. In this lecture, yeah, we will talk about the unconstrained first-order methods and the unconstrained second-order methods. We'll see. So the second order means that we are basically restricting locally the function to be the second order Tailor expansion, which means that the function is approximated using a quadratic, and kind of the first order part is linked to the gradient, or the Jacobian, in this case the gradient, and the second order part by the Hessian matrix. And we will see that we can also approximate the Hessian matrix, basically using like some kind of finite differencing scheme, and that's the Bfgs algorithm. And then we'll talk about constraint optimization. We'll just kind of pause what the KKT conditions are and what is the thing. We'll talk about duality, but we won't really see some algorithms there to solve things. We just kind of mention them. And coming back to our autonomous driving problem, as I said, so you might have like the optimal trajectory problem might be posed as an optimization problem. The learning of the perception task, so minimizing the neg log likelihood, or minimizing cross entropy for like a decision task, whether maybe you might be interested like knowing whether this is a bicycle or this is a pedestrian or this is a car. And so this is a classification problem, and there the loss function might be the cross entropy loss. Okay, so that's for the outline. And let's dive in the first part. So optimization is about finding optimum, and there are two kinds of optimum. Either it's a maximum or it's a minimum, depending on our semantic that we associate with the cost function or with the function, the objective function. So in machine learning and in robotics and control, we are usually talking about finding minimas. The cost function has to be minimized and the loss function has to be minimized. But if we are in optimal decision, then we might maximize the reward function, or we might have different functions that we instead try to maximize, and usually the relationship is just that one is the negative of the other. Yeah, so first question is, what is the minimum of a function? So if we have a function like that, we have two minimas and one maximum. And which ones would you say which one would you say is the global minimum? The one on the left, yeah. So this one here, this is the global minimum, at least on that domain. And what do you think is the definition of a local minimum? A local, yeah. Hmm? Yeah. Yeah, that could be a basic definition for what a local minimum is. And with your definition, we just need a notion of neighborhood. And let's say a local minimum is within that neighborhood, the point that has lowest value, function value in that neighborhood. And we don't need to go through like derivatives or whatever. So that's actually a good definition. And then the function that's drawn here is a polynomial. It's a fourth order polynomial. And it has a global minimum here. But since it is smooth, the gradient can help find the direction of the minimum. And that's really the key difference between continuous optimization and the other types of optimization, is that we're going to be able to use gradient information in order to find these points, the orange points. It has another local minimum, so the one on the right side, the orange one. And the way that we would solve for all the stationary points in these, because this function is continuous, and this is a technique that you guys have seen in high school, so I hope, so this is should not be a surprise. We just set the gradient of the function to 0, and then we solve for what points actually solve that. And then the way we can go further to see if it's a global or local minimum, if it's a minimum or a maximum, is we will look at the sign of the second order derivative at that point. And so we basically reduce the search of minima points to solving a linear equation, or, well, to solving an equation. It's not linear in the parameter because we have x to the power 3, x to the power 2, and so on. But instead, we are looking for a solution set of an equation. As I said here, so this is note, so the sign of that equation here tells us if the stationary point is a minimum or a maximum. So that's the basic idea that guides continuous optimization, and we will kind of try to develop that in the higher dimensional case and see what that is. So the first algorithm that you usually derive so the first thing that we should note is that this notion that we can have access to an algebraic equation which is going to specify the stationary points, it's not going to be the case when we have a crazy objective that we're optimizing that is very nonlinear and so on. So that's why people have developed gradient descent. I think I also talked in the linear algebra lecture that when you have a linear system of equations that is gigantic, so let's say you have thousands and thousands of decision variables. Inverting the matrix, I think it's something like quadratic in the number of columns or something like that. I don't exactly remember the complexity. It's in the slides. Using the Gaussian elimination algorithm basically becomes impractical. So it will not converge in time. So what people do is they basically define an objective for how to invert the matrix, and then use gradient descent in order to invert the matrix. So what we're going to see, gradient descent, is not only the idea of optimizing functions that are highly nonlinear and so on. You might actually optimize linear functions, but where the number of decision variables is so large that solving in closed form is not even possible. Okay, so you've all seen, I think, things like that, where here we have a quadratic function. We are initializing the search here, where we are computing a gradient direction, and we're trying to find the minimum, actually the global minimum that's here. quadratic actually have closed form solutions. And so this is just an example of typically using a gradient descent algorithm where we would have a closed form solution. Okay, so let's consider the following problem. So in unconstrained optimization, we're just trying to find a vector, a Euclidean vector, that minimizes the objective, and that's it. We don't have constraints on like what the, maybe like some bounds in which the vector should stay or something like that. We don't have anything like that. We are just minimizing the objective. And note, maybe this is something that I didn't say, we are going to be interested in optimizing functions that map to the real, and that's where the cost function and the loss functions and so on are defined. So we're optimizing a function of many variables to a scalar. So we assume f is differentiable, and the gradient descent algorithm functions this way. So x here, this is x2, and this is x1, and x is a vector, so a point here. And the way it works is, at this point xi in time, we query the gradient, okay? So this weird notation with the transpose, depending on the authors, I said this in the vector calculus lecture, but either you have a column vector defined for the gradient or you have a row vector. And here they define the gradient as a row vector in the book, and I followed the convention from the book. So it's a row vector, transpose becomes a column vector, and then we can just add it to x, to the state vector. Okay, so the gradient is telling us what is the direction of maximum increase. So if we're here, the gradient is telling us this is this direction here, is the direction of maximum increase. So that's why we descend the gradient. We flip the sign, and that tells us the direction of maximum decrease, and we just apply a step in the direction of the gradient. So just from here to there, and by applying that update rule recursively, we end up at the minimum. So you can see that this is not going to work for all classes of functions. You're going to end up in local minimas. If your function has local minimas, you're going to end up in a local minimum. There's one important thing, which is the step size here, which is alpha. And we're going to talk about what we can do for alpha. Yeah? If the function is increasing,
yeah, it's increasing, and the computing, no, it's decreasing, the function is decreasing, then the gradient will show the direction of maximum decreasing, no?
No.
That's not just the gradient.
It's negative of the gradient. It's going to point you to the decrease. The gradient, by definition, it's just a definition thing. So remember that we talked about partial derivatives as defined, like on the left side you have the thing that's after, and you do minus the thing that's before.
Okay.
And then you divide by the step, and then you take the limit of that. That's the notion of partial derivative, or derivative in general, with the second thing. And what this basically tells you is the coefficient of the tangent at that point. And then when you have a function that takes multiple inputs, you can compute that for all the different inputs, and that becomes your gradient. And yeah, and then this is giving you the direction of maximum increase, just by definition. We could have defined the gradient to be the maximum decrease, but this is not what this is. This is why we talk about gradient descent. We can also talk about gradient ascent, which is when we are maximizing functions, and then you just add the gradient to the state vector. I think the gradient thing, like why it's the direction of maximum increase, is not easy to wrap your head around. But I don't want to dive deep into what, like all the possible different ways of defining the gradient. But what you will see next week is something called a natural gradient. I think I talked maybe about this. I'm going to talk about it today again a little bit. The idea, one definition of the gradient is that it is the direction of maximum increase within some small step, and you arrive at the same kind of conclusion that then the partial derivative second line definition. But how you measure that small step, how much you move, in the gradient case is simply the Euclidean distance. And in the general case, you might want to measure how you measure distances in your vector space with a metric, with an inner product, with different inner product. And in that case, you obtain what is called the natural gradient. And the natural gradient is simply multiplied by the metric tensor that we saw in differential geometry. So all that stuff is not easy to wrap your head around, because there are two ways you can define the gradient. Either you say it's the direction of maximum increase of the function and you derive it from there, but that's not how you're taught in school, because that's too complicated to understand. So usually you're taught by the more simpler, straightforward way, which is the second line. But these definitions end up at the same point. Yeah. Okay. So yeah. So in this case, the gradients are, well, I think in all the cases, are orthogonal to the contour lines. That's also important to understand that. So you could see these contour lines, and then in gradient descent, like the gradient is basically bouncing against the contour lines, right? Okay. So this is just the numerics of the graphical examples that we are looking at. So we have a two-dimensional quadratic, and these are the coefficients that I use to plot this. And you can compute the gradient of a quadratic. That's easy when you're given the definition like that, right? Because so it's the sum of two parts, and we have a 1/2 convenient here. So the gradient of that expression is, if I call this matrix A, the gradient of that expression would be AX, two AXs. And then the 2 cancels out with the 1/2 conveniently here. And then because the derivative of the sum of two terms is equal to the sum of the derivatives, we just have that the derivative of that, which is a linear function, is just the coefficient here. So that's our gradient. So you have the gradient expression, and we can then query using the closed form expression of the gradient, what the gradient would be at every single point. And we set a starting point, and we fixed step size of 4.085 here. And then, yeah, what you see is that here we have kind of a thin valley, and the gradient descent algorithm is basically zigzagging here. That's a little bit of a problem here. So the first thing we can consider is the step size what can we do with the step size? Having a good step size is actually important for faster convergence and convergence altogether. If it's too small, we are going to be slow, and if it's too large, we're going to fail to converge. You can see that if the step size is too large, you query the gradient at some point, and then you're going to move past the local minimum, and then you're going to pass it again, and then pass it again, and you're never going to dive into the local minimum. And if it's too small, you're basically going to take many increments and take forever to reach the local minimum. So the first thing we could do is we can normalize the gradient and just use the direction that the gradient is using, and then try to come up with a step that's optimized for that particular query, for that particular kind of curvature landscape that we are navigating. So that's the realm of adaptative method. What they do is, the key idea is that if f is increasing, we will decrease alpha, and if f is decreasing, we will increase alpha. So you pick a direction, and you see that f is basically increasing from where you are. F is increasing. What you do is you decrease alpha, and then you see, it's decreasing, but it's still increasing from where I am. You try to decrease alpha, and you requery the function, and then you decrease alpha until it decreases, and then you make that step. So that's adaptative because you will query maybe multiple points along that direction that's given by the gradient until you kind of decrease the function. So you adapt the step size. If the function decreases, then you might want to increase the step size such that maybe you dive deeper into the local minimum. That's the idea. So coming back to this notion that we can optimize systems of linear equations using gradient descent when they are already too large. So a system of linear equation, you can just write it ax is equal to b, where A is a matrix, and x would be your decision variable here. To solve that practically using gradient descent, you would say ax minus b is equal to 0, and find an approximate solution, meaning one that minimizes the difference between ax and b in terms of the least square norm of the difference. So you minimize the norm of the vector ax and the vector minus the vector b, and eventually they will converge. So yeah, you can write down this equation using the matrix form equation. And so you get the gradient expression this way. So that's the gradient with respect to x. And then the speed of convergence of gradient descent applied to the system of linear equation is going to depend on something called kappa, which is the ratio of curvature, which depends on the direction, and it kind of corresponds to our notion of a narrow chasm. So in the quadratic thing, you saw that there's this basin at the end, but the basin can be kind of more like roundish, which would mean you have kappa is equal to 1. Or it can be much more kind of elongated, like an ellipse, like a really elongated ellipse, in which case kappa would be really large. Like kind of infinite would be kind of like a line, right? And that has to do with the curvature, because with the notion of narrow chasm. So if kappa is really large, what you have is you have basically a valley and then kind of a narrow thing down there. And if this thing is kind of going down, then what gradient descent has to do is basically get in the narrow chasm and then kind of navigate until it reaches the end. But for the gradient, for the adaptative method, it's going to be well, if you don't have an adaptative method, you have constant step size, it's too big, you're basically going to get stuck, you're going to stop there. But if you have an adaptative method that always decreases the steps, if you increase the function value, you're going to end up with these tiny little steps navigating the narrow chasm forever until you reach there. So the higher the kappa, so the ratio between the highest eigenvalue and the smallest eigenvalue of the matrix, the longer it will take to optimize the problem. Okay, so that brings us to backtracking line search. And that just, it's a concrete way of implementing that idea that basically you're picking the direction that has to do with the gradient by normalizing the gradient itself, and then multiplying the gradient, then trying to find along that line what is the optimal alpha, so step size, that you would take, and then stop from there and then query another time the gradient. So the procedure, this intuitive procedure that I described is implemented in backtracking line search. And the way you stop backtracking line search is by checking the Wolfe condition. So note here that if you want just more text about that, you can go to this PDF from Marc Toussaint, who used to be a professor here. And he updated his lecture slides in the summer last year, so they're quite new. The way he presents this lecture, this is also the same kind of content, is instead by starting by vector calculus and going from there and seeing how linear algebra connects to vector calculus. So the idea is really to focus on continuous optimization. Yeah, so what you have here is a point evaluated, a function evaluation here. And this here is the first order linear approximation of the function. And this line here is a little bit different because you kind of increase the coefficient, the coefficient of the line. Okay? All right. So in line search, what we're looking for is an alpha. So little delta is our direction. It's the normalized gradient. We are looking for an alpha such that we minimize the function value, and actually this should be over our domain. So the key idea of backtracking line search is to start with a large alpha and then go down. That's why it's called backtracking. We just go from large values to smaller values. And we decrease by a factor that we called this guy, this symbol here, alpha, as long as the function value is greater than the linear, the first order Tailor expansion of the function at that point, at x, where we added this coefficient here to the line here. And you can use you could use 1 here, but realistically you would never kind of find queries where you would accept basically the update. So the idea is to relax a little bit that thing that you're getting better than the linear approximation. So by in order to relax that, we add that coefficient here and we end up with this line. So the key idea is that we are going to compute an alpha, an original alpha that's here, and this is above what we would get with the linear here. We fixed this number here to be A, and with the difference between the linear approximation to f and the value that we get by increasing, by having an alpha step size would be this here. The idea is that we decrease alpha, so then we're here, it's still bigger. We decrease alpha, still bigger. We decrease alpha, still bigger. And then eventually we end up here, tack, and we accept the update. So that's the idea of the Wolfe condition. So what that coefficient actually is a minimum, here is a minimum decrease, a minimum desired decrease for f. Okay, so if we get in the ideas of backtracking line search with gradient descent, we end up with the following algorithm. So what it takes as input is we have a vector in the space that we are looking for at an initial value. We have the function, we have a way to query the gradient at any point of the function. We have a tolerance with which we want to get out of the algorithm, and we have parameters, and we initialize the step size to 1. So the way gradient with backtracking line search works is by computing the normalized negative gradient and then performing the backtracking line search, which is this part here, checking the Wolfe condition, which is this, and decreasing the step size if the Wolfe condition is not met. We can also not have the Wolfe condition, and in that case would just be like, are we decreasing the function value at all? And we accept as soon as we are decreasing the function value. Here it's a little bit more aggressive in the sense that we want to have a minimum decrease. Or, yeah. And yeah, once we found what alpha would be, we just applied our update to x. So remember that delta here is the negative normalized gradient. So we just add the alpha times the step. And then we might have something that makes sure that alpha never gets under a certain value. So we basically set alpha to be the minimum between this and delta max here. Well, here we are not using delta max because we set it to infinity. So we can set delta max to something like that would be the minimum kind of step size that we would get. Oh, yeah. I don't know, it's not so clear here what delta, because we don't modify this and we don't modify this, so whatever. I think I should change this algorithm here. Okay, so when the step size is below some value, we stop. So it basically means we are in a local minimum. And actually in continuous optimization, this step here, this condition here, is one of the most difficult things to set up. It's really difficult to set up when to stop. So this is kind of an arbitrary thing that we are just implementing right now. But you have to see that in the most advanced numerical optimization software, this is always kind of, what do you put there? And it really is a little bit problem dependent. Okay, so comparison with and without backtracking line search. So here we have our quadratic example. And you see that if we do have backtracking line search, so here we're like going Basically, this is going down, and this is going up again, and then we're landing here. Instead, here, this is, because it's already kind of going up, starting here, right? Just, because of the curvature of the function. So this is already kind of going up. And so the backtracking line search will stop here and requery the gradient, which means that the direction is going to deviate a little bit towards the minimum. Yeah. So it's going to change the behavior of the algorithm in terms of the trajectory that it's following in state space. Yeah. Yeah, so you see here there's this command, perhaps you actually only do 10 iterations. So it's the parameter to stop the optimization, to conclude that you're in a local minimum. So one typical way is just to measure what's the norm of the gradient at that point. If the norm of the gradient is really, really small, you're saying, okay, it seems that we are like basically reaching a local minimum, but then what would be that threshold? What would be the norm with which you decide, okay, that's a local minimum? Another way is like this thing. So it's saying if you don't make any progress with your step size and you're like really kind of like fiddling around the same point, then you stop. Another thing would be you only have like a certain budget dedicated number of iterations for your algorithm, and then you stop. So it's a termination condition. That's really difficult to set, and because it has to do with constants that come up out of thin air, and you have to find those. So here, theta is a tolerance. What should theta be? It's kind of arbitrary. Okay, so another thing is that we might want to do is something called momentum. So the key idea is we should be able to use memory to deal with narrow passages. And you could see that as a kind of higher order method, but in time, not in terms of the geometry. And the idea is to dampen the oscillations. So you remember from the differential equation lecture, damping means, if your system is not damped, then you oscillate. And if your system is damped, you kind of like, you don't oscillate. So this is exactly that is being implemented in momentum methods. And the corresponding update is like that. So you basically have your gradient descent update, and then you simply add a little bit of the update that you used in the previous step. And so you define that delta I to be, well, the previous update, so meaning the difference between what is your state and your previous state. And the difference between those is basically your update. And so you can identify, so that this was basically your previous update. So it's this part, but from the previous time step. So you see this I minus 1, I minus 1, I minus 1. So that's it. So you basically keep a little bit of the update, of the previous update in your current update. And that's called momentum. And so what you can see is that so it's kind of like linearly combining the update with the previous update and the previous update. And so it's less aggressive in terms of the zigzags. I mean, that's one way to see it. But the thing with momentum, and I think in this particular case, it's actually not as good as gradient descent, is that when you arrive to the local minimum, because you have momentum. Momentum means, I mean, in physics, it's basically like you're keeping, part of the kinetic energy that you're having. You have to kind of fight against it. And so when you arrive at the local minimum, it will overshoot, and then you have to come back. Right? So that's, I think, the big problem with momentum things. But that intuition that you have in 2 dimensions here, if you're in extremely high dimensions, like a neural network you're optimizing for millions of parameters, might not actually hold. So yeah, a lot of the intuition that you build from 2D problems and you move on to 1,000,000 dimensions don't hold anymore. And a big discussion at like machine learning conferences is why optimizing neural networks with gradient descent even actually works. And a lot of the discussion is, well, it could be that there are many local minima in optimizing large, high-capacity neural networks, but that all these minimas are the same. They are kind of all global minimas. And that's kind of the discussion. If that's the case, then using a local method for optimizing these gigantic functions really makes sense. If every local minima is kind of at the same depth as the others in terms of risk, then you don't have to use any global method to optimize your network. And actually you can't, because the number of variables that you're dealing with is way too high. Okay, so stochastic, but so far there's no theorem like that says that. It's just like a conjecture that people have and are kind of working, mathematicians are working towards this idea. So stochastic gradient descent. Yeah, so this is the thing that's being used in optimizing neural networks. And that's because the neg-log likelihood objective has a specific shape or specific structure. So, okay, when you're optimizing for a machine learning problem, typically like a neural network that has to minimize risk over a data set. You have combinations of input-output pairs, and what you're trying to do is minimize the risk on every input-output pair. Yeah, so what I want to say. So in these cases, you have to imagine you have a model that's producing a decision variable, and then you have a loss function that's on top of that. And the way you can see the objective function, or like the structure of the objective function, is you have the input, a model that generates the output, the pair that goes with that output generates some little loss function, and that loss function is added to all the input-output pairs into one single scalar. And that scalar is going to be the average loss over the entire data set. It doesn't matter if you have 1 billion samples, the structure is going to be this kind of tree structure coming to one single scalar variable. So the way that stochastic gradient works is, so that's the shape of the loss function. It's the sum of these little loss functions that you have. So you have your neural network produces a prediction, compares the prediction with something from the data set, which is like a constant at that point, and then you sum all these branches into one scalar. And that's the head that I'm describing. It's the sum over all the little n, where n might be a million, a billion, or whatever is the size of your data set. Because it has this structure where everything is combined as a sum at the end, and in machine learning, this would typically be the negative log likelihood. Doesn't really matter, but that ln is the negative log likelihood, and you're summing over the entire data set. The corresponding update for gradient descent would be to update the parameters of your model, based on the sum of the gradients of all these different L's that are these different branches that are being combined. So the key idea is that you can compute your gradient over small subset of big N. So instead of computing your gradient over, let's say you have 1 million input-output pairs, you select a chunk, maybe 500, and then you compute your gradient there. And then you select another randomly selected 500, and you compute your gradient there. So you're going to have an estimation of the gradient that is wrong because your gradient includes the sum over 1 million data samples. But computing one gradient evaluation for 1 million data samples, maybe your model predicts a full image, like a full, I don't know, like 1 million pixel prediction. Maybe that's what your model is doing. So doing that 1 million times is not possible. I mean, the computational cost of doing that is really crazy. So you compute this noisy gradient evaluation by computing the gradient on a subset of your data set, hence the name stochastic gradient, because it's a noisy evaluation of the gradient because it's an approximation of the gradient. And yeah, so that's basically what's driving deep learning under the hood. It's stochastic gradient descent, and there are many variations of what to do, momentum and all that stuff that we just saw, to then add to the stochastic gradient evaluation. But this notion that you select subsets, this notion is called mini-batch, and it's the idea of selecting random subsets from your Ln objectives and evaluating those. And the larger the mini-batch, the more accurate your gradient is going to be, but more costly it is to compute. So basically, if you have a time budget, let's say you want to optimize for 1 week, then having very large but costly to evaluate mini batches is going to lead to you performing less gradient descent steps, but more accurate ones. Whereas if you have smaller but more noisy gradient, so smaller mini batches which leads to a more noisy gradient evaluations, you're going to be cheaper and you're going to be evaluating more gradients, but they're going to be more noisy. The nice thing about stochastic gradient descent, as you saw, there's still in optimizing deep networks, there's this question whether how good are the local minimum. But there are still some, you can still get stuck in local minimum if you don't choose, or something that's not even a local minimum, but if you choose the parameters wrong and you evaluate with noisy gradient, you might get stuck. And actually noisy gradient has the other property that it can get you out of local minimas. So, yeah. There's really this problem to understand what is the shape of the optimization objective for neural networks that is still not scientifically well understood. But what an advantage of stochastic gradient descent in the general case is that because the gradient is noisy, you might get out of local minimas just by kind of fiddling around, because the gradient is a little bit noisy, so you move yourself out of the local minima. Okay, so this was just using first order information. What we saw is that we can just use the direction from the gradient and then adapt the step size using backtracking line search. We might evaluate noisily the gradient if we can decompose the gradient as a sum of, or the loss function, as a sum of loss terms. And if we evaluate on a subset, then this would be stochastic gradient descent. Now, what about the curvature of the function? Is this going to help us? So you probably all heard about the Newton method for optimization. The Newton method for optimization comes from somehow the Newton method for finding zeros of a function. And you probably all saw that, but I'm going to summarize it again for you. Does somebody not know that method or has never heard of the method of the Newton method for finding zeros of a function? You never heard of it? Okay. And you've heard of it? Okay. So the key idea is that you start at a point, compute what the tangent is, compute the intersection with the zero line, right? And then you repeat that process over and over again. And you repeat that process by starting here again. And the key insight is that when you're going to overshoot on the left side of where the function crosses the zero line, you're going to compute the tangent, and it's going to bring you on the other side again. And so that has the property to converge to the zero. So you compute the tangent, intersection with the zero line, then compute the tangent again. Eventually you cross the function, and then there, the tangent brings you back here. And then you go left, right, left, right, left, right, and you converge to zero. That's the kind of the key idea. So it's for finding zeros of a function from usually just a function from the real to the real. And so we have the equation of the tangent, which is the first order Tailor expansion of the function here. The way to see the first order Tailor expansion of a function is to say we shift the function so that we put the zero at x0. So let's say that this is x0. We shift the function so that the function is centered at x0. Now, f of x0 is going to be our offset with respect to the zero line. And f prime is simply going to be the coefficient of the line. Okay? So you can see the Tailor expansion like that. We look for xi that crosses the x-axis. And now, in order to derive the method, we just set x to be xi plus 1, sorry, x0, so this guy, to be xi, and y to be 0. So what that means is, given the first order Tailor expansion of the function at point xi, solve it such that the linear the first order Tailor expansion has a point that is x0. Sorry. What point xi plus 1, for what point xi plus 1 does the first order Tailor expansion get to 0? Okay? That's just what this equation is saying. And then it's just linear algebra, and then you get that. Does that make sense, that derivation? So by iterating this process, by saying, compute the Tailor expansion, where does it cross the x-axis, recompute the Tailor expansion, where does it cross the x-axis, compute the, and so on, this eventually converges to the 0 point. So that's the Newton method for finding zeros of a function. What does that help us with continuous optimization? Well, you can apply that to the first order derivative of the function. And what are you going to get? You're going to get stationary points of f. So if I replace f by f prime, I'm going to get stationary points of f. And now, I just have to filter for not getting the maximas, but instead getting the minimas. Or, if I'm in the case where the curvature of the function is always positive, meaning that I'm in kind of like a kind of descending function. If I iterate this, the stationary points that we get are always going to be local minimas. That's convex functions, but we're getting there. So, yeah, so we can use that method for finding roots of a function and apply it to the to f prime, and what we get is called the Newton optimization method. And what you see, what appeared there, of course, because f prime was already there, so what we get is the second order derivative, and that's why we are in the unconstrained second order methods. And so in high dimensions, we can apply the same process of Tailor expansion, iteratively computing the Tailor expansion of the first order derivative of the function. And that's the second order Tailor expansion of the original function. And that is the Newton method. We can identify that to the gradient descent algorithm. And what you find is that there's no step size here. Because we are basically jumping to, what that Hessian does is allows us to jump to the 0 point, to the stationary point of the approximation of the function. So there's no step size. And that's the big benefit. What basically the Hessian does is compute, warp the direction and compute exactly what the step size is. So another way to see this method is to say, we construct a second order Tailor expansion at a certain point, and then there's a closed form solution for what the minimum of a second order quadratic, of a quadratic, and we just use that and jump to the minimum of the quadratic approximation at that point. And then we iterate. We construct quadratics, construct the next quadratic, construct the next quadratic, and so on. So this is, of course, kind of only works when the Hessian is symmetric. So there's a bunch of restriction on what the function shape should be. It should be symmetric. We actually assume that the Hessian is positive definite. And yeah, so that thing that I was explaining, we can view the Newton method for optimization in a different way. So we can view it as saying, we make a second order Tailor expansion at a particular point x, and that is what that is here. Then we set the gradient with respect to the step size to 0. That means we're looking for the stationary points, but not the gradient with respect to x, the gradient with respect to the step size. So don't be confused here. So the gradient is the gradient with respect to x, and here I specified we are looking at the gradient with respect to the step size. So we are setting the gradient with respect to the step size equal to 0, and we want to solve that algebraic equation. Now, when we do this, the gradient with respect to x of f of x is going to be constant when we are deriving with respect to delta. And same thing with the Hessian. So solving that, we get that this thing is a constant. This thing is a first order with respect to delta. So that's what we get here. And this whole thing becomes the Hessian times delta. And then we get the Newton step again, but from a different angle. So the other one was we had an iterative procedure for finding the zeros of a function, and we applied that to the first order derivative. Now the thing is we simply take the second order Tailor expansion and solve for the minimum of the Tailor expansion of the quadratic there. But it's the same thing. It's just two ways of viewing it. Okay, so talking about natural gradients, one way, and you'll see that next week, one way to view the Hessian here is that it acts as a metric to define properly the direction. So you could view like the a quadratic as a surface, and then the Hessian there acts as, like, so for example, if your Hessian has this like high kappa, then you're actually having like a curved kind of space, and you're going to then measure distances differently depending on whether the function increases a lot in a certain direction or is very flat in the other direction. So basically, that's how you can also view this Hessian, as measuring distances. If n is a second order polynomial, then the Newton step just jumps directly to the minimum. So the quadratic thing that we saw in the beginning, we could just solve it in one step with a Newton step. Okay, so what would then be a way to apply that in a more general case, where all the assumptions that we have for positive definiteness and so on don't really apply, but we still want to apply this. What we would do is we would damp the matrix such that we make sure by computing a minimum lambda here that it is positive definite, and kind of in the limiting case this would just be the identity, so we'll fall back to the gradient descent case. But when we are nicely positive definite, then it would kind of converge to the Newton method. We would apply line search with the Wolfe condition, and and that's it. So that's the kind of typical Newton method that you have implemented kind of everywhere. Okay, what about when you don't have access to the Hessian? And that's, you can approximate it. The idea is that you get a data set of points and gradient evaluations at previous iterations and use that to approximate the Hessian. So if you are given two of these points, like x and the gradient of f at x for 2 points, for x1 and x2, you can kind of approximate it with like a second equation type of thing. And so if I pose that y is gradient at x2 minus gradient at x1, you suppose that x1 and x2 are close. That's the idea. Or they are like neighboring points. What would be kind of the simplest approximation of the Hessian matrix? You can pose that h is equal to delta, delta being the difference in the point. You can view delta as being some kind of approximation of the gradient itself there. So the Hessian would be Hessian times delta, or this approximation would be equal to the difference in gradients. And you can derive the following. So here we just apply kind of this rule over and over and over again. So we apply it one first time. This thing here is just a scalar, so we just shuffle it and put it on the other side. And we multiply, from this line to this line, we multiplied by y on each side. And then this thing is just a scalar, so we put it on the other side, and then we divide that outer product of y by the scalar thing. What this ends up being is a symmetric rank 1 solution for H. That key idea that we can use differences in gradients to approximate the Hessian, this is the key idea of quasi-Newton methods. And this leads to the Bfgs algorithm. And so now we have the same kind of algorithm as the Newton algorithm, but instead of having H, instead of relying on the fact that we can compute the Hessian, which in large cases might be completely prohibitive. I mean, you've never heard of like computing Hessian on a full neural network. Sometimes, but it's so expensive that usually you don't do it. So there are many cases where computing the Hessian is just prohibitive, very difficult to do, and instead we can approximate it with this scheme. It's called the Bfgs, and the LBFGS, which you probably heard about before, is just the idea of limiting the rank of H by kind of throwing out some information and storing kind of a minimal set of vectors. So, because this increases in memory over time. That's the idea. So you can limit the memory. Okay, I'm running out of time, so I want to talk about constraint optimization. The key idea of constraint optimization is that you want to have inequality and equalities defined directly on the state variable. So the key idea, like if I would say I want to optimize that cost function within such that I remain within that box, and of course the solution will be that point here. That would be a box constraint on the state variable, and you could model it with saying it's everywhere 0, and outside of the box the constraint is infinity, and I will add that function to the objective, and that would be a valid objective. So you have your inequality constraints that are defined this way. You have one for the upper part, one for the bottom part, one for the left part, and one for the right part. And you can combine all these 4 different constraints in order to define the inside part of the box. And you can just add these kind of infinity constraints to your objective. That would be kind of the most intuitive way of just going by with constraints. But this doesn't optimize super well, and these infinity penalties, because how do you even define the gradient for like infinite values? So we can overcome this issue by introducing something called the Lagrange multipliers and the Lagrangian. And so this looks like this. So you have the function value, and we add the constraints to the objective, multiplied by something called the Lagrange multiplier, and it's this guy here. And so we have a number of inequality constraints, and we can pack them into one single vector constraint, and then we have a vector of Lagrange multipliers, and our inequality constraint then maps to our M instead of mapping to R. Instead of having like a collection of inequality constraints, we just have one vector valued inequality constraint. So an important notion, and that's really tricky to explain in 15 minutes, but whatever, it's what it is, I'll try, is the notion of duality. So what I just explained is called the primal problem. It's the problem of having a function, an objective function, together with constraint functions. And the constraint functions, if they are negative, we absolutely don't care. But if they are positive, then we need to push the solution back into the constraint, which might be a box, might be whatever. It's not necessarily something that linear. X is called a primal variable. Duality, and there are several notions of duality, especially there's weak and strong duality. Duality means that associated to that, we have something associated to the Lagrangian. And it's called the dual problem. And it means that the solution to the primal problem, I mean, duality is about saying that the solution to the primal problem is equivalent to the solution to the dual problem, meaning that it's equivalent to maximizing the Lagrangian with respect to the Lagrange multipliers, where the Lagrangian is itself minimized with respect to the primal variables. Okay? And there we have a constraint on the dual variables. The Lagrange multipliers are also called the dual variables. The constraint is that they have to be all positive or zero. That's important. They can be zero, meaning that the constraint might be inactive. So what is then strong and weak duality? The first point is that primal values are always greater or equal to dual values. And the second point is that the notion of weak duality is that minimizing the maximizer of the Lagrangian with respect to the dual variable is always greater than maximizing with respect to the dual variable, the minimizer of the Lagrangian. So that stems from the kind of minimax inequality. So here we could spend time trying to explaining why that is. There's a very intuitive way of seeing that. Maybe the best is that you read that little part in the PDF to understand that. It's just one page. Try to lock that down. For your general knowledge. I don't think that's going to be so much a big part of the test, but I think really understanding that is really important for understanding optimization. So why weak duality actually holds, and that holds for any function. And then there is strong duality. Strong duality means that the solutions are equal. And that holds for a class of functions, which are the convex functions. And we'll talk about what convex functions are right now. But just before I say that, if it's easy to solve the Lagrangian with respect to the primal variables, then solving the dual problem is super easy. Because maximizing with respect to the dual variables, to the Lagrange multipliers, is just a linear function. So the dual problem is just linear in the. So the Lagrangian is just linear in the Lagrange multipliers, right? Okay, we can also have problems with equality constraints. That just means that on top of these G functions, we have these H functions where we are defining them to be, the constraints is that the functions have to be equal to zero. We can also offset that so they can be equal to whatever, but in the general case, we set them equal to zero. We typically assume that F, G, and H are differentiable functions in continuous optimization. But F, G, and H can be non-convex and non-linear. In that case, we talk about something called a non-linear mathematical program or an NLP. In mathematical programs like that have continuous and equality and inequality constraints, I think here it's only for the inequality case. The key inside this is the key inside of the KKT conditions, is that our objective is giving us a direction, minus f here, that we're trying to optimize. And at the optimum, the constraints, the active constraints, the active inequality constraints, are pushing against whatever the objective is pulling on. And the lambda, the Lagrange multipliers associated to each of the constraints. So here you have a constraint, a red constraint, and a blue constraint. And anything that's white means that there's no active constraint at that point. Anything that's red or that's blue means that this is not part of the feasible set associated to the optimization problem. The Lagrange multipliers are the variable such that the linear combination between the gradient of the of the inequality constraint is exactly equal to the gradient of the cost function, of the objective function. So yeah. So that's the key insight of the KKT condition, which is summarized here as a theorem. So given the mathematical problem, we have Lagrange multipliers for the equality and the inequality constraints. So the inequality, it's the lambdas, and the equalities, it's the kappas. And we have the KKT conditions are coming. There are 4 KKT conditions. The first one is stationarity, which is the one that we just illustrated with this drawing. It means that the gradient is equal to the negative, or the negative gradient is equal to the linear combination of the gradient of the active equality and inequality constraints multiplied by their lambdas and kappas. That's stationarity. Primal feasibility, well, that's obvious. It means that all the constraints have to be satisfied. That's easy. Dual feasibility, also kind of easy. So all the Lagrange multipliers of the inequality constraints have to be 0 or positive. And complementarity is more tricky. That's the notion that the product between the inequality constraints and the Lagrange multipliers has to be 0, meaning that either a constraint is inactive, meaning its Lagrange multiplier is 0, or a constraint is active, or a constraint is active, and meaning that you have to be at the boundary. So G has to be 0. So this is summarized. I just summarized the 2 most important ones. The stationarity condition, which is that the gradient has to be in the span of the gradients of the inequality and equality constraints, and lambda and kappas are the coefficients associated to the vectors here. And the complementarity constraint, which is the 4th one, is kind of the logic constraint activity. So either lambda is 0, meaning the constraint is not active, or G is 0, meaning you're at the boundary. Okay, so we have a few minutes to describe convexity. First, a convex set. So when we are optimizing convex functions, we are talking about convex optimization problems. There's a whole book on convex optimization that is like a Bible that a lot of scientists know. It's not only computer scientists, but convex optimization is a really big part of science, modern science. Goes beyond, like it's also all sorts of scientists, engineers use convex optimization. So you have to understand what convexity is. So a convex set is simply a set for which the linear interpolation between 2 points of the set, also all the points on the linear interpolation, belongs to the set. The straight line between 2 elements of the set is in the set. That's a convex set. Yeah. So just a point, in the case of strong duality, that the primal and the dual solutions are the same, that holds for convex optimization altogether. So duality is then very important for convex optimization. So convex sets are not very interesting. What is interesting is convex functions. So let be a function whose domain is a convex set. Then the function f is a convex function if for all x and y in the domain, and for any scalar between 0 and 1, we have the following. That is that if we interpolate between the 2 points, if we query the function at an interpolation between the 2 points, we'll get that the interpolation of the values is larger than the function value at any point there. It's easier to visualize that equation by thinking f is a convex function if and only if its epigraph, which is this here, the epigraph of a convex function. The epigraph is this green part. above is a convex set. So you can, if the convex set that is defined by everything that is above the line defined by the convex function, that also holds for high-dimensional cases, if that thing is a convex set, then you have a convex function. So in the case of convex functions, it means that at any point, the Tailor expansion is always under the function values. That's another way to view convexity. Another way to see it is that the Hessian is positive definite everywhere. This is an example of a convex function that you can look on your own because I don't have time anymore. But basically, x log x is the negative log likelihood function that we use in machine learning. And it's a convex function, and you can see kind of why and what I said. So like this is the Tailor expansion at any point, and you can kind of get the idea that if I compute the Tailor expansion at any point, all the point in the Tailor expansion will always be under whatever the function is. Okay, so two very important class of programs. There's the linear program, linear programming, which is the following. So you have the objective is a linear function. So C is a constant, and X is the variable that we're optimizing for, and it's subject to some linear constraint, linear inequality constraint. This is known as a linear program. And we can compute the Lagrangian of that thing. And because this is convex, we have a strong duality. So it's equivalent to the following dual problem. So maximize, instead of minimizing with respect to the primal, we maximize with respect to the dual. And the constraints that appear here, the first one is the stationarity constraint, right? Because it means that the gradient of the function here, the gradient is C. The gradient of the function plus the gradient of the inequality constraint times the dual variable is equal to 0. That's the stationarity constraint. And then that thing here is the third, on the second, it's the, oh, that's actually the third, right? Because I said primal feasibility was the second. It's the third KKT constraint is the dual feasibility. If you look at a linear program, the way that the linear inequality function work is by defining some kind of polytope in space. And so one class of method for optimizing such functions is by walking around these constraint points. So, I mean, you can use whatever you want for optimizing this. You can use some kind of like interior point gradient method. So an interior point method would be that you kind of define like barrier functions to stay inside the polytope, and then you have a gradient method that drives you towards the minimum. But an older class of method is called the Simplex Method, where the key idea is to walk around these vertices here. So you explicitly define the constraint set, and then you walk around it and find the minimum. Why? Because the minimum is always going to be at one of these vertices. Or in extreme cases, degenerate cases, is going to be the whole line. Another class is the quadratic programming problems. And instead, here we also have linear inequality constraints, but we have a quadratic objective. And yeah, this is called a quadratic program. We can also compute the Lagrangian. and then extract the dual problem. And here we have the function f of the dual variables. And in terms of KKT, the constraint is simply the dual feasibility. And an example would be, so we define, like we have a quadratic and we define a box using the inequality constraint, and then there the minimum is here, so it's not on a vertex, and we cannot use a method like the simplex method. We'll use something different. Okay, so coordinate set is a powerful algorithm for solving optimization problems. Basically, we have issues with the direction and the step size. We solve the direction method using the gradient, and the step size using the backtracking line search. If available, second-order information gives a much better direction. That's called a Newton step. And we can always approximate the curvature using the second method, and that gives the class of these Bfgs method, the quasi-Newton method. If we consider the additional constraints, the solution must obey the KKT conditions. There are 4. The 2 most important are the stationarity condition and the fourth one, the one that has to do with the inequality constraints. And in the case of convex, objective, and constraints, we have strong duality. And so sometimes solving the dual problem is actually easier. And we can develop efficient algorithms for different classes of problems. So for example, for linear programs, we might explicitly define the constraint set and walk over the vertices of the constraint set. But we can also define other types of algorithms, such as like interior point methods, that are basically going to be walking inside the constraint set using barrier potentials or things like that. Okay, that's it. Any questions? Yeah. Well, yeah. So next time, the students who are the TAs that were doing the tutorials are going to present some problems where we extract material from the lectures and show how it goes in context with respect to machine learning and robotics problems.